Alright, in this video we're going to be looking at probability distributions. And what we'll do here is we'll define a random variable, and we'll look at two types of random variables, both discrete and continuous. We'll look at some of the requirements for a probability distribution, and we'll look at some of the parameters that involve a probability distribution, usually the mean, median, and mode. And then we'll look at the range rule of thumb. And also we'll look at the ways to determine whether the results of probabilities are usual or unusual. Alright, so what I need to define first is a random variable. A random variable is a variable. And of course, a variable, if you recall from algebra, is nothing but a letter that's used to represent an unknown. So in this case here, we'll be using x as the unknown. And it is a variable that has a single numerical value. And that numerical value is usually determined by chance. Okay, so a random variable is nothing but a variable that has a single numerical value that is usually determined by chance. Now, random variables can be one of two things. It could be either discrete or it could be continuous. Okay, so a discrete random variable it has a collection of values that is finite or countable. A discrete random variable is either finite or countable. It's a collection of values. In this case, if you like x is equal to 1, 2, 3, 4, 5, and so on, those are discrete random variables because those variables, those values are finite and they are countable. And then the second is a continuous random variable. Something that's continuous, that means that it has infinitely many values on a continuous scale, and it's not countable. Okay, so here in a continuous random variable, it has infinitely many values that are on a continuous scale. Okay, and usually with a continuous random variable, that variable is going to be in the form of a decimal or a fraction. So we'll just say as a decimal, usually it's going to be continuous because it's on some continuous scale. And usually continuous could be something that can be measured to a precise value. Okay, so pretty much know the difference between a continuous random variable and a discrete random variable. And in this case here, I have some examples of just this. Let's say we want to determine whether the value is a discrete random variable, continuous random variable, or not a random variable. Okay, based on those definitions. So in part A, we have the amount of snowfall in December in city A. Now here the amount of the snowfall can be measured to a precise amount. Okay, because we can measure snowfall as, let's say, 8.4 inches of snow in December. So in this case here, this would be a continuous random variable, because of the fact that we can measure the amount of snowfall. Part B is the number of textbook authors now sitting at a computer. That's something we can count. We can count the number of textbook authors at a computer, so this would be discrete. Part C, the response in the survey to the survey question, did you smoke in the last week? This one would not be a random variable, and the reason for that is, did you smoke in the last week requires a yes or no question. It does not require a numerical value, whether it's discrete or continuous. So this is not a random variable. Not a random variable, because it's just giving us a yes or no answer. Alright, part D, the number of light bulbs that burn out in the next week in a room with 15 bulbs. That's discrete, because we can count how many light bulbs that burn out. So this will be discrete. Part E, the time required to download a file from the internet. Time is measurable. We can measure to a precise minute, well, precise minute, also precise seconds. So in this case here, this is continuous. And then part F, the weight of a T-bone steak. Well, the weight can be measured to a precise number in pounds or in ounces. So here, that would be continuous. Okay. So pretty much you know the difference between what's continuous and what's discrete. Okay. Alright, the next thing I'll talk about is a probability distribution. Because that's what this section is all about. Now, probability distribution is a description that gives the probability for each value of the random variable. Okay. Usually it's this description that gives the probability for each value of the random variable. And we can express a probability distribution. It is expressed as a table, a formula, or a graph. Now the ones we'll look at are the ones that are going to be expressed in the form of a table. So you'll know what a probability distribution will look like. Okay. Alright, now there are 3 requirements of a probability distribution. So on the next sheet, let me give you the requirements of a probability distribution. So here there are 3 requirements of a probability distribution. 1, there is a numerical random variable called x, and its values are associated with corresponding probabilities. Okay, so there is a numerical random variable. We're going to call that x, and its values are associated with corresponding probabilities. That's the first requirement. Now the second requirement is this. The sum of all the probabilities must be equal to 1. So I'm going to use the Greek letter sigma for the sum of all the probabilities must be equal to 1. Now, sums could be 0.999 or 1.001, and that's due to rounding errors. But the sum of all your probabilities must be equal to 1. And then third, each individual probability value must be a number between 0 and 1, inclusive. Okay. And that's for each value of the random variable x. Okay. So for each value of the random variable x, each individual probability value must be a value between 0 and 1, and that does include 0 and 1. So for you to have a probability distribution, it must meet all three requirements. Otherwise, you do not have a probability distribution. Okay. Alright, the next thing I want to talk about is the parameters of a probability distribution. Okay, so let's move this up. So we have parameters of a probability distribution. I'll just say parameters here. Now the parameters that we're going to be dealing with are the mean, the variance, and standard deviation. Okay. Now, when we're dealing with the probability distribution, we're using parameters instead of statistics. So, with the mean, the formula we're going to be using is the Greek letter mu, because it's a population mean, and that's equal to the summation of your individual x value multiplied by its corresponding probability value. That will be the mean of a probability distribution. Now for the variance, the one that I'm going to be using is this formula. That's sigma squared. And that's equal to the summation of x squared multiplied by p of x. And then that sum is going to be subtracted. We're going to subtract the square of the mean, which is your mu squared. That's going to be subtracted from the summation of x squared times p of x. Now, once you know the variance, the standard deviation is very simple, because standard deviation is nothing more than the square root of this. So this will be the square root of this part that's going to be underneath the radical, the summation of x squared times p of x minus mu squared. Okay. So once you know the variance, the standard deviation, you just simply take the square root. Now in problems like these, you are going to just find just the mean and the standard deviation. So the standard deviation, you'll just use this formula that has the square root. Okay, so now let's look at a few examples of just this. And before we look at that, let's look at the round-off rule. The round-off rule is always going to be to one more decimal place than the number of decimal places for the random variable x. So you'll round to one more decimal place than the number of decimal places used for the random variable called x. Okay? So your random variable is to a whole number, then you'll round your answers to one decimal place. Okay. Alright, so let's look at a couple of examples of just this. Now let's say we had this. 5 males with a particular genetic disorder have one child each. The random variable x is the number of children among 5 who inherit the genetic disorder. Determine whether the table describes a probability distribution. If it does, find the mean and the standard deviation. Well, let's look at the requirements here. Each x value has a corresponding probability value that's given here, as you can see. So requirement number 1 is met. Now for requirement number 2, we have to take the sum of the individual probabilities here. So here you have to add 0.4182 to 0.3983 plus 0.1517 plus 0.0289 plus 0.0028 plus 0.0001. And you do come up with 1. And as you can see, I've already added those numbers up and came up with a sum of 1. So requirement number 2 is met. Requirement number 3 is also met as well, because each of those individual probability values are between 0 and 1. So in this case here, I do have a probability distribution because all 3 requirements have been met. Okay, and then from here I can go ahead and find the mean and the standard deviation. Okay, now here's how I'm going to set this problem up. The first column is going to be my x values. The second column will be p of x. And I'll go ahead and write down my x values, which is 0 all the way up to 5. And then write down the corresponding p of x values here. This is, the first one is 0.4182. For 1 is 0.3983. For 2 is 0.1517. For 3 is 0.0289. For 4 is 0.0028. And for 5 is 0.0001. Okay, so that's x, and then that's p of x. Now my next column is going to be x times p of x. And then the next column will be x squared. And then the last column will be x squared times p of x. Okay. Now here's what I'm going to do here. X times p of x is this. I'm going to take each individual x value and multiply by its corresponding p of x value. So 0 times 0.4182 would be 0. And then 1 times 0.3983 would be 0.3983. Then 2 times 0.1517 would be 0.3034. And then 3 times 0.0029 would be 0.0867. And then 4 times 0.0028 will be 0.0112. And then 5 times 0.0001 will be 0.0005. Okay, so you can see the x squared times p of x column is completed. Now for the x squared, I'm going to square each individual x value one by one. So 0 squared, or 0 times 0 is 0. 1 squared, or 1 times 1 will be 1. 2 squared will be 4. 3 squared is 9. 4 squared is 16. 5 squared is 25. Okay. Now for x squared times p of x, each number in the x squared column will be multiplied by its corresponding p of x value here. So in other words, if I do 0 times 0.4182, that's going to be 0. If I do 1 times 0.3983, that would be 0.3983. And then 4 times 0.1517 will be 0.6068. And then 9 times 0.0289 will be 0.2601. And then 16 times 0.0028 times 16 will be 0.0448. And then 25 times 0.0001 will be 0.0025. Okay, now, here this table is complete. Now, here's how I'm going to find the mean. Alright, the mean is this. That's mu is equal to the summation of x times p of x. Well, look what I got. X times p of x, that's this column right here. What I'm going to do here is add up these numbers in this third column here. So when I add up these numbers here, I'm going to get 0.8001. But my x value is a whole number, so I'm going to round this to one decimal place, which would be approximately 0.08. I'm sorry, 0.8. Not 0.08, just 0.8. So the mean there would just simply be 0.8. Now for the standard deviation. Okay, for the standard deviation, that sigma is equal to the square root of the summation of x squared times p of x minus mu squared. And in this case here, notice that I have the x squared times p of x column here. All I need to do is add these numbers up, and that would give me this part right here. So if I add these numbers up, I'm going to get 1.3125. That's what x squared, that's what the summation of x squared times p of x is going to be. So here, sigma is equal to the square root of, this part is 1.3125 minus mu was 0.08. So this will be 0.8. So that's going to be 0.8, and you're going to square that. Now this we can type into the calculator, and we're going to have to round that off to one decimal place as well. So in this case, here's second x squared for the square root, and then 1.3125 minus 0.8, and then x squared for the square, and then close your parentheses, and then hit enter. Okay, to one decimal place, that will be 0.8. So that standard deviation there is 0.8. Okay, so that's how we use a probability distribution to find the mean and the standard deviation of that distribution. So the mean there is 0.8. and the standard deviation will be 0.08. Okay. All right, let's look at another example. Ted is not particularly creative. He uses a pickup line: if I could rearrange the alphabet, I would put U and I together. The random variable X is the number of girls Ted approaches before encountering one who reacts positively. Determine whether the table describes a probability distribution. If it does, find its mean and standard deviation. Okay, so in this case here, we can see requirement number 1 is met, because you can see there that each numerical random variable has a corresponding probability value associated with it. Okay, now requirement number 2, the sum of the probabilities must equal to 1. So if I add 0.001 to 0.016 to 0.128 and 0.216 and 0.508, you're going to get 0.869. That's less than 1. So here, the probability, sum of all the probabilities must equal to 1, and it does not. So we can stop right here and say that this particular table does not describe a probability distribution, because requirement number 2 is not met. So here, I'm going to say requirement number 2 is not met, because the fact that the sum of all your P of X's is 0.869, which is not equal to 1. So here, we can just say not a probability distribution. Okay, and we end this problem right here, so there's no need for us to find the mean and the standard deviation, because this one does not qualify as a probability distribution, because requirement number 2 is not met. Okay, the next example is this. In the accompanying table, the random variable X represents the number of televisions in a household in a certain country. Determine whether or not the table is a probability distribution. If it is a probability distribution, then you're going to find the mean and the standard deviation. Alright, so here's your table here. We can see that for each individual random variable, there is a corresponding probability that is associated with that random variable. And then the next thing we need to do is find the sum of those individual probabilities. They must equal to 1. So in this case, if I do 0.05 plus 0.08 plus 0.32 plus 0.34 plus 0.11 and then plus 0.10, you'll see it does equal to 1. So requirement number 2 has been met. The sum of all your probabilities does equal to 1. And each individual probability is between 0 and 1. So we do have a probability distribution. So we can go ahead and find the mean and the standard deviation of this set of data. Okay, so like I did in that first example, I'm going to have X and P of X. I write my X values here from 1 to 5. And then my P of X, this is 0.05. 1 will be 0.08. And 2 is 0.32. 3 has 0.34. And 4 is 0.11. 5 is 0.10. Now these decimals are going to be more friendly than the ones that I did in the other example. Alright, so in this case here, x times p of x, and then x squared, and then x squared times p of x. As you know, for x squared times p of x, we multiply the x value by its corresponding probability. So 0 times 0.05 is 0. 1 times 0.08 is 0.08. 2 times 0.32 is going to be 0.64. 3 times 0.34 will be 1.02. 4 times 0.11 will be 0.44. And 5 times 0.10 will be 0.50. Or you can say 0.5 if you want to. Now for the x squared, I'm going to square each individual x value. So 0 squared is 0. 1 squared is 1. 2 squared is 4. 3 squared is 9. 4 squared is 16. 5 squared is 25. And then finally for the x squared times p of x, we take your x squared, multiply by its corresponding probability. So 0 times 0.05 is 0. 1 times 0.08 is 0.08. 4 times 0.32 will be 1.28. And then 9 times 0.34 will be 3.06. And then 16 times 0.11 would be 1.76. And then 25 times 0.10 will be 2.5. Now I'm going to sum up the third column and the last column, because that's what's going to help me find the mean and the standard deviation for this particular probability distribution. So in this case here, to find the mean, that's mu is equal to the summation of x times p of x. Well, add up x times p of x, that's this column right here. That will tell me what the mean is. So if I add this up, I'm going to get 2.68. So that mean there will simply be 2.68. And if we round this off to one decimal place, it'll be 2.7. So the mean for this probability distribution will be 2.7. Now for the standard deviation. That's this. Sigma is equal to the square root of the summation of x squared times p of x minus mu squared. What I need to do is sum up the x squared times p of x column. Add those numbers together, you're going to get 8.68. That 8.68 is what the sum of x squared times p of x is going to be. So in this case here, when I do the standard deviation, that would be the square root of the summation of x squared times p of x. That was your 8.68 minus mu was 2.7, and that's going to be squared. Now again, you can enter all of this into the calculator. So in this case here, second and x squared, and then 8.68 minus 2.7, and that's squared, close parentheses, hit enter, you'll get, let's say the one decimal place, 1.2, because 1.178 rounds up to 1.2 to one decimal place. Okay, so the standard deviation there will be 1.2, and the mean there will be 2.7. Okay, so that's how we find the mean and the standard deviation of a probability distribution. Okay, now there's one more thing I need to cover, and that is dealing with probabilities that are going to be unusually high or unusually low. Okay. So here I'm going to talk about an unusually high number of successes. Okay. If you have X successes among N trials, that's going to be an unusually high number of successes if the probability of X or fewer successes is unlikely with a probability of 0.05 or less. So in other words, if you have a probability of X or more, and that probability value is less than 0.05, then you have an unusually high number of successes. Okay. And then the other one is the unusually low number of successes. And X successes among N trials is an unusually low number of successes if the probability of X or fewer successes is unlikely with a probability of 0.05 or less. So if you have the probability of X or fewer, and that probability value is less than 0.05, then that's unusually low number of successes. So in this particular situation, let's say we had this example. The accompanying table describes results from 8 offspring P's. The random variable X represents the number of offspring P's with green pods. Here you want to complete parts A through D. And in part A, you want to find the probability of getting exactly 7 P's with green pods. Okay, now I realize this may be a little bit difficult to see, but I will rewrite this. And then P of X is 0 plus. And also this is 0 plus, meaning that the probability value it's a very small value, but it's not equal to 0. It's a little bit more than 0. So here for 2, that would be 0.002. For 3 is 0.027. For 4, that would be 0.085. For 5, that would be 0.174. For 6, it will be 0.359. For 7, it will be 0.255. And 8 will be 0.098. In this case here, we want to answer part A by finding the probability of getting exactly 7 P's with green pods. Right, so in this case here, exactly 7, it would be this number, 0.255. So to answer part A, I'll write this off to the side, the probability that X is equal to 7 would be 0.255. Okay, so that's the answer to part A. Part B asks this. Find the probability of getting 7 or more P's with green pods. Now, 7 or more, if we were to write that in symbolic notation, would be this. Greater than or equal to 7. So the probability that X is greater than or equal to 7. Now, looking at this table right here, we only got 7 and 8. So we just need to simply add the probabilities of getting exactly 7, probability of getting exactly 7, plus the probability of getting exactly 8. Okay, so in this case here, the probability of getting exactly 7, we found that out to be 0.255, plus the probability of getting exactly 8 would be 0.098. So if we add those two together, you'll get 0.353. Okay, so that's part B. Now part C asks this: which probability is relevant for determining whether 7 is an unusually high number of peas with green pods? The result from part A or part B? Okay, in this case here, we have to use part B, because the reason for that is this: the criteria for determining whether a number is unusually high or unusually low, it has to be X or more, or X or fewer, which does include that value. X or more means greater than or equal to. So we have to use the answer in part B. Now part D is this: is 7 an unusually high number of peas with green pods? Why or why not? Well, 0.353 is bigger than 0.5, so it is not unusually high. The 7 is not an unusually high number because of the fact that 0.353 is bigger than 0.05. Okay, so pretty much be familiar with your probability distribution tables and how to interpret probabilities and determine whether a number is unusually high or unusually low. And that will complete this video on probability distributions.